Okay, let's unpack this deep dive. You've sent over some really fascinating material about using Google's Gemini API
Hmm.
and specifically how to kind of get it working with data, right?
Right.
What really jumped out at me was this focus on interacting with databases.
Yeah, bridging that gap between the AI and structured data.
Exactly. We've got code snippets here showing, well, first connecting to the API, which is step one.
Standard stuff, yeah. Getting the credentials sorted.
Right, and then listing the available models, and wow, there's quite a list.
There really is. You got the familiar ones like Gemini Pro, but then these others.
Yeah, like Gemini 2.5 Pro XP 0325. Sounds
It,
very experimental.
it likely is. And the Flash models, and even some specifically for tuning, ending in tuning.
Right, we'll get to that tuning part later, I think. You also showed how to get details on a specific model, like Gemini 2.0 Flash,
Uh-huh. Looking under the hood, basically. Things like its token limits.
which was huge, wasn't it? Over 1 million.
Yeah, pretty substantial input limit.
Yeah.
And also what it supports, like generate content or count tokens.
So the big picture here, it seems, is exploring how these AI models can understand and query data. Specifically, this street lamp data set from Switzerland you included.
That's the goal. Taking this real-world example.
So our mission today is really to map out that whole process using Gemini to access, analyze, and maybe even, improve our understanding of this kind of data.
And seeing the tools Gemini offers for that. The variety is key, from the general Pro models to the faster Flash ones, and then those customizable tuning options.
Each with different strengths, I guess. Power versus speed versus specialization.
Pretty much. And knowing those limits, like the token count for Gemini 2.0 Flash, gives you a feel for the scale you can operate at. It's all about understanding the potential, but also the boundaries.
Okay, now here's where it gets really practical, I thought. You actually took a CSV file, just a plain text file, basically.
Yeah, full of data on these Swiss street lamps.
Right, packed with details, IDs, names, location, down to the municipality, the street.
Coordinates the operator.
Hmm.
CKW in this case.
And you laid out how to create an actual SQLite database from it.
Yep, streetlamps.db.
Yeah.
Taking that raw data and structuring it.
And you even put it all in a table called lamps. We see you ran a quick query too, right? To find out how many lamps are in Adlitonville.
Uh-huh. Just a quick select count.
And the answer was 1279. That's a lot of lamps.
It is. But it just shows, how you instantly make that data queryable. You transform it.
It's that first crucial step, turning a data dump into something useful.
Exactly. And that structured format is what the AI can then, hopefully, interact with more effectively.
Okay, so to make that interaction happen, you define some specific functions, like translators almost.
That's a good way to put it. Tools for the AI.
First was listables. Simple enough, just shows the tables available.
Which is just lamps in this case. Gives the AI a map.
Then describable, using lamps as the example, that gives the schema, right? The column names and types.
Yep. It shows that lampenit is text, Langengrad, that's longitude is a real number, and so on. The blueprint, like you said.
And the third one, execute query. This sounds like the powerhouse.
It is. That's the function that lets the AI actually run SQL commands.
And get results back. You showed an example getting the distinct municipalities.
Mm-hmm. A select distinct schemata from lamps.
And it was a long list.
Okay.
Adligenswil, Aish, Ebicon, lots of Swift places.
Mm-hmm.
But it ended with a weird one, none.
Ah, yes. None. That's almost certainly missing data in the original CSV.
Ah, okay. So some lamps didn't have a municipality listed.
Looks like it. A very common real-world data issue. Something the AI needs to potentially handle or be aware of.
So these three functions list, describe, execute. They're the building blocks for the AI to talk to the database.
Precisely. Map, blueprint, and the tool to actually retrieve specific bits of information based on the user's question.
Right. So putting this all together, you're basically setting up an AI assistant. You even gave it a name, GeoLite Info.
Yeah, just a system instruction, really, telling the model its role.
And you told it can use those database functions we just discussed.
Correct. Giving it the tools it needs.
And we see examples of chatting with it, asking it to list tables. It does that. Describe the lamps table gets that right too.
Standard checks, making sure the plumbing works.
Then a more complex question. Are Teilgemeinde and Gemeinde, submunicipality, and municipality always the same?
Uh-huh. A question requiring data comparison.
And if not, list the differences.
Oh.
The AI figured it out, right? Said they aren't always the same.
Yeah, it correctly identified pairs like Altishofen, Eberseken, and Luzerne-Litau where they differ. It would have needed to run a query for that.
Which it did using the execute query tool.
Presumably, yes. It translates a natural language question into a SQL query, executes it, and then formats the answer.
And the last example query, which municipality has the fewest lamps?
Another one needing a query grouping by municipality, counting, and finding the minimum.
And the AI came back with Hochdorf with only one lamp.
Correct again. So it shows the potential, using just plain English, to interrogate the database via the Gemini API.
It's pretty cool. Instead of writing SQL, you just ask.
That's the promise, making data access more intuitive, especially for people who aren't database experts.
Okay, now, things pivot a bit towards a much harder task, it seems.
Prediction.
Predicting the Swiss municipality just from coordinates and a street name?
Right. Input like longitude, latitude in the Strasse.
You sampled the lamp data to create test sets for this. We see an example input, longitude 8.36 something, latitude 47.07 something, Streetdorf Udligensweiler star.
Yep. Trying to get the AI to guess the Gemeinde from that info alone.
And you tried getting a baseline prediction using different Gemini models, sometimes with instructions, sometimes even letting it use Google search.
Exactly. Trying various approaches with the general purpose models first.
And the results, the accuracy for this baseline.
Not great. Really quite low. Around 1.28%.
Wow, 1.28%. Even with Google search helping.
Even with search. It suggests this is a pretty tricky task. Maybe slight variations in addresses or the coordinates not perfectly matching administrative boundaries. It's complex.
That low number really highlights it, doesn't it? The general models just aren't specialized enough for this specific Swiss geography puzzle.
It seems that way. Which naturally leads you to think about, well, specializing a model.
Fine-tuning. So you use that Gemini 1.5/001 tuning model base.
Right. To create a custom model specifically for this task.
And the input for tuning was that location, string, longitude, latitude, street.
The input prediction, yeah. Paired with the correct output, the Gemeinde, lots of examples.
So you're essentially training it on the street lamp data itself, showing it. For this location info, the answer is this municipality.
Exactly. Teaching it the specific patterns in this data set.
And you kicked off a tuning job and eventually got back a custom model ID, something like Tuned Model Schweizgemeinde Prediction Model 52JPC.
That's the one. Confirmation that the tuning process completed and created a new specialized model artifact.
So the moment of truth, evaluating this tuned model.
Putting it to the test.
You gave it a new address, one it hadn't seen during tuning. And the tuned model, using that specific ID, it correctly predicted Malters.
Okay, so a positive single data point there.
But then you tested it on a larger sample from your data, and the overall accuracy.
Still pretty low, around 2.56%.
2.56%. So better than the baseline 1.28%, roughly doubled, but still not exactly stellar.
No, far from it. And you mentioned seeing quite a few incorrect predictions or even errors where it couldn't give an answer.
Yeah, the evaluation details showed a lot of misses.
So it learned something, but maybe not enough, or maybe the data had inconsistencies. Needs more work, clearly.
But here's an interesting wrinkle. The token usage.
Ah, yes, the cost aspect.
You found the tuned model used way fewer input tokens compared to the baseline model that needed detailed instructions, like 535% fewer in one example.
That's a huge saving on the input side, because the tuning baked the instructions in, essentially.
Right, but strangely, the output tokens were higher for the tuned model in that same example.
That is interesting. Maybe it was more verbose in its prediction, or less confident. Hard to say without seeing the raw output.
Yeah, it's a trade-off. Lower input cost, potentially higher output cost, and only a modest accuracy gain so far.
It really highlights that machine learning, especially tuning, involves these practical compromises. You gain something here, you might lose something there, or the gain isn't as big as you hoped initially.
So wrapping up this whole deep dive then, what are the sort of main takeaways from walking through all this material?
Well, I think you've clearly shown the whole workflow, end to end. Connecting to the API.
Getting data into a database.
Making the AI talk to that database using functions.
Testing baseline performance.
And then attempting that fine-tuning for a specific tricking task.
Even if the final accuracy for the tuned model wasn't, a game changer this time.
Right. The process itself is valuable. It demonstrates the potential for using LLMs to work with structured data in new ways.
That natural language querying part still feels really powerful, making data exploration potentially easier for more people.
Absolutely. Lowering the barrier to entry for data analysis could be a major benefit.
And okay, for you, the learner listening to this,
Yeah.
You've seen the steps involved now, right?
Yeah.
Setting up the tools, trying out the training.
And that low initial accuracy, that's not failure, that's just opportunity.
Yeah, it points to where you could explore next. Maybe different ways to format the input data.
Or tweaking the tuning parameters, using more data,
Yeah.
cleaner data.
Lots of avenues. And that token saving with the tuned model, even with low accuracy, that's important too.
Definitely. It hints at potential cost efficiencies down the line if performance can be improved. Cost is always a factor with these powerful models.
So it leaves us with some big questions to mull over, doesn't it?
It does. Like, what are the next logical steps to actually improve this municipality prediction?
Could you bring in other data sets, maybe boundary maps or something?
How much difference would better prompt engineering make for the baseline models? We saw it wasn't great here, but maybe there are better ways to ask.
And maybe stepping back, what are the bigger picture implications of AI making predictions based on location like this? Any ethical things to consider?
Always important to keep those in mind as the technology develops.
So, yeah, this deep dive laid some really interesting groundwork. Feels like just the start of exploring what's possible here.
A solid foundation laid.
Mm-hmm.
Plenty more to build on. Thanks for sharing all this material. It's really insightful to walk through.